It is my absolute pleasure to welcome Chelsea Scott and Cassie Brigham. They are part of the Open Topography project, which has been a wonderful project that's been at the San Diego Supercomputer Center in partnership with Arizona State University and several other collaborators for this large initiative. And Open Topography facilitates efficient access to topography data, tools, and resources to advance our understanding of the Earth's surface, vegetation, and its built environment. So welcome, Chelsea and Cassie, to get us started.
Perfect. Thank you. And thank you all very much for the invitation to speak here. Cassie and I are very happy today to tell you our works specifically on topographic change within Open Topography. And so I'll speak for about the first 10 or so minutes, and then Cassie will speak for the remainder of the time. And here is an outline of our presentation today. So we'll start with an introduction to Open Topography, and then we'll go over the basics of LiDAR, which is the type of data most commonly hosted by Open Topography. And then we'll go over what is vertical differencing. Just to get you started, this is a method of seeing how the Earth's surface changes over time. And differencing has many different prominent sources of error within the results, and so we'll discuss some of these examples. And then Cassie will take us through her new geostatistical error method. And she'll begin with a theory discussing the uncertainty and quantifying that in topographic differencing. She'll go over a Python tool that she's developed, and then she'll conclude with applying her method to the Eaton fire in Los Angeles early last year. So to begin, we're going to discuss open topography, LiDAR, and topographic differencing. So to begin, what is open topography? Claire gave a short introduction, but our goal is to democratize, essentially make it easy for people to access high-resolution topography data. And so these data are big, they're complicated to use, and you need high compute power to really do much with them. And so Open Topography's goal is to make it easy for people, students, faculty, researchers, as well as the general public to easily use these data in whatever their applications are. I invite you to check out our website, opentopography.org. So who we are, we're a fairly small team. There's 8 of us. We all have, though, different jobs, and so none of us work full-time for Open Topography. We were founded in 2009, and we are at 3 institutions. The lead institution is you guys, the San Diego Supercomputer Center, and Vishu Nandagam is the lead there, and then Min Fan also works there. And then we're also at EarthScope, and then Cassie and I are at Arizona State University. And there is a picture of the supercomputer. A little bit of that runs Open Topography. And we are very grateful for our support from the U.S. National Science Foundation. It has allowed us to continue to grow and develop new tools since 2009. There's Vishu. So in more detail, what do we do? So the main goal is topographic data hosting and distribution. And then we want to take those data and make them easy for people to use, coming in at a variety of different levels of earth science and compute skills. And so we make it easy for people to access a variety of commonly used products that can be generated from these data. So this includes maps of elevation, and then different products to easily visualize these maps of elevation. We also have ways for people to access these data when they're interested in bigger portions of the data, for example, with APIs, notebooks, and open source code. And we also are continuously running different education and training. We have different webinar series and we give short courses at conferences. And these are really a great way of introducing graduate students to Open Topography so that they can really use these data in their graduate research. So now we're going to get into the LiDAR, into the data that OpenTopography hosts. So most of our data are LiDAR. And LiDAR stands for light detection and ranging. And there's an example of an airplane that is taking a LiDAR dataset with a laser scanner. And this airplane essentially measures the two-way travel time between the airplane and then the ground surface using a laser pulse that is typically of near-infrared light. Then with knowledge of the airplane's position, we can convert those measurements to elevation and horizontal location. And this can then give us often sub-meter measurements of elevation. LiDAR data for many scientific applications is collected with an airplane, but there's other ways it can be collected via terrestrial LiDAR, mobile LiDAR, satellite, and handheld platforms. And there's many applications of LiDAR. Perhaps at least most commonly seen in Phoenix are self-driving cars, and they use LiDAR sensors to help navigate. iPhones also have a LiDAR app that you can move around and get a LiDAR data set of your room or outside area. LiDAR is also very commonly used in industry for building and land surveying. And then within many applications, academic, insurance, among others, LiDAR is important for mitigating the impact of natural hazards. And so there's two main data sets or data types that LiDAR can be distributed in. And the first one that I'll discuss is point clouds. And so point clouds are sets of X, Y, and Z measurements. They're not on any particular grid. They're just irregular measurements. And each of these points typically has a classification. So here's an example of a point cloud you can see in Lower Manhattan. And here on the left, that's showing the buildings. These LiDAR point clouds can be classified. So in that case, the classification indicates what the feature on the ground represents. In most common classification is either unclassified points versus ground points. So here in Manhattan, we see that the buildings are gray. So they are unclassified, although to us they look like buildings. In this case, the blue is the water and the pink is the noise. And there's really a lot of points in these data. Typical modern data sets are anywhere from 10 to 60 points per meter squared. So you can really get into the hundreds of millions of points fast, which is why using high performance computing resources is important. And then here on the right, you can see that same area, but this case, those brown points represent the ground. We've removed the buildings and the ground points are often really important for earth science applications. So these point clouds can then be transformed into gridded data sets or digital elevation models. And so these are continuous gridded surfaces of the elevation. And there's two common forms of these used in the earth sciences. The first is a digital terrain model. So this is a grid of the bare earth or the ground surface. So here on the left, we can see that we've taken just the ground points and we've gridded that into a digital terrain model. The other type of grid is called a digital surface model, abbreviated DSM, and this measures the top of the landscape, which includes the top of buildings and vegetation. And so in this case, we can see here in this grayscale map, which is called a topographic hillshade, you can see the footprints of the buildings very clearly. And then what Cassie and I have been working on quite intensely for almost the past decade is vertical topographic differencing. And the goal of this approach is to see how the landscape has changed over time. And over time, that's by looking at the change in landscape between two different LiDAR acquisitions. And many LiDAR data sets were acquired in the past decade or so. So now I'll walk you through how this happens. So to do differencing, we begin with the point cloud from the earlier data set. We can see there in all those blue points. And then can have a point cloud from the second time or the post-event data set. In the literature, these can be called the compare and the reference. And just quickly note that the second one has many more points, and this reflects the fact that data sets often get denser over time. The next step is to take both of those point cloud data sets and to grid them. And so here you can see in this, the blue is the low elevation, and then the yellow represents the high elevation. And then the next step is a subtraction. So the difference or change is going to be the reference, which is the second data set, minus the first, which is the compare. And then we typically display these where red indicates that the ground surface moved down between the two LiDAR acquisitions, and blue indicates that it moved up. In a little bit more detail, this is a pixel by pixel subtraction of the two digital elevation models. And it looks like a pretty simple equation, but in detail, it requires really a lot of careful preparation of the data, as well as careful management of the noise in both of the data sets. So I'm now going to show you several examples of topographic differencing. So here we're looking at an example of Yosemite, California. And the two grayscales are topographic hillshades, so images of the digital elevation model from before, first right there, and after there, a rock fall. And then in the color map, you'll see that the red is downward movement of the Earth's surface. And so if you look here, you'll see this red, and that represents the loss of rock and trees during a rock fall. And so these data are collected by the National Park Service because they are interested in monitoring rock falls and making sure that people stay safe despite this geologic hazard. Oh yeah, there, just in a little bit more detail, to recall that the red indicates that the service has gone down between the two captures of the LiDAR data. And here is another example. This is looking at the airport in Salt Lake City. And we see those two grayscale maps, and they show the airplanes have moved. And then we can use the topographic differencing, which shows airplanes in different locations between the two acquisition dates. And in fact, the blue airplanes are airplanes that were there during the second acquisition, and they reflect the sort of artificial upward movement of the ground surface due to the presence of the aircraft. And here is the last example that I'll show you. So this, we're still looking in Salt Lake City. And we see two grayscale images. The first shows no housing in this area. The second shows a lot of houses. And then the map, the change shows blue. And those blue represent an increase or new housing developments. And so these topographic differencing results can really nicely show us urban growth and changes to the urban environment. So one of the activities that OpenTopography recently engaged in was developing topographic differencing tools. And the first one, as shown here, was on-demand vertical differencing. And the goal is that in just a few mouse clicks, a user with no particular expertise in geology or geospatial work could come in and run a topographic differencing. And we were interested in developing this for several reasons. First, we wanted to standardize an approach for doing this topographic differencing analysis. Second is we wanted to make it easy for people with different expertise to do differencing. And then third, and we really needed to figure out how to programmatically solve different challenges in getting the data ready for differencing. For example, putting the data in the same coordinate reference system. And coordinate reference system is essentially a fancy term for the type of address that you use to locate the data. And we overcame several challenges. First, the algorithm had to be able to work with older data sets and different types of data sets. The algorithms had to work on demand, so they essentially needed no human input and really could almost never fail. And then the algorithms had to interact with the cyber infrastructure and HPC resources. And here are the images, data sets that can be used for differencing in OpenTopography. So there's about 3,000 data sets that cover over 20% of the lower 48 of the United States for differencing. And then there's many data sets in New Zealand. And interesting from a geologic perspective is that these data sets collectively cover a lot of different geologic processes. All right, and now it is Cassie's turn.
Okay, so Chelsea has shown us how we can make some really beautiful differencing maps, but we're kind of left with the uncomfortable question, how much of that difference that we see is real and how much could be error? So here I have an example of topographic differencing from Northeast Virginia between a data set from 2012 and one from 2019. And what's being differenced here are the digital surface models, so the ones that include the vegetation and buildings, et cetera. We see areas in red. Sorry. Yes, areas in red where trees have been cut in between the two captures, and you can also tell that in the pan over with the hillshades. We also see areas in blue where trees have been replanted and grown. Areas with no change are shown in white. And so we can see that differencing is great for seeing these large scale changes with the DSM. However, let's take a look at the digital terrain model. So again, using just those ground points. And the scale of the change is going to be much different. So for the DSM, we were looking at changes on the scale of meters to tens of meters. And now we're going to be looking at centimeters to tens of centimeters. So we can begin by noticing some natural change. So like river incision and aggregation. We can also notice change from humans. So the creation of building sites. The change, and then across the whole map, we see that there is kind of an overall lifting of the ground surface. Most of the map is blue. And so that begs the question, are we actually looking at real change? Like, there's been some large geologic phenomena in Virginia that we didn't know about, or is it due to error? And so the more likely scenario is that this is in fact error that is compounded from the differencing of these two data sets. So here's the fundamental equation we need to keep in mind throughout the rest of the talk. So observed change, so the change that we see on the differencing map, is the true change plus error. So every pixel in our differencing map contains some combination of real surface change and measurement error. The entire challenge and the focus of a lot of our work is separating these two components. So not all error types are created equal, and understanding kind of how they're structured in space is key. So Random error, so coming from individual laser pulse noise, for example, are scattered independently. And we see that on the left here of this figure. So think of it like static on a TV screen. There's no pattern, there's no structure. These are actually easy to deal with statistically because they average out over large areas. The ones that are more tricky are systematic errors. So they have spatial patterns. So a pixel that has a certain amount of error, the pixels next to it are more likely to have that error. And these can happen on different spatial scales, or what we call ranges. So these errors are correlated in space, and that correlation means that over large areas, we can't just average them out. So we need to figure out a way to deal with them. So I'll walk you through the main error sources organized by spatial scale that we find in differencing in LiDAR data sets. And the idea of spatial scale is important because our method works precisely by decomposing error at these different scales. So at the long range, so we're talking about kilometers and beyond, we encounter systematic calibration biases and most dramatically vertical coordinate reference system errors. So these are errors in metadata recording. If one dataset uses a different geoid model, or worse, has ellipsoidal heights recorded as orthometric heights, you can get uniform offsets of centimeters to tens of meters across the entire area. So here is an example of an 18-meter offset in Washington State. The entire landscape appears to have gone up by 18 meters over time, which is obviously a metadata error, not a geological catastrophe. LiDAR data are collected as the aircraft flies back and forth in parallel strips, kind of like mowing a lawn. Each strip is called a flight line. If the GPS positioning of the aircraft drifts slightly between strips, you get systematic offsets between adjacent swaths. In the differencing results, these show up as alternating bands or stripes, typically a few centimeters in magnitude and hundreds of meters to kilometers wide. These stripes don't represent real ground change. They're artifacts from the data collection geometry. They're insidious because they can mimic or mask real linear features in the differencing results. Another very common problem is horizontal misalignment between two data sets. So here on the right, we see a hill slope with a landslide. So in T1, you have the intact hill slope, and in T2, you have the hill slope after the landslide. And so if they were perfectly matched, the apparent change that we would see would be equal to the real change. However, if you think of if you take T2 and slide it slightly over from T1, then you'll see in the topographic change graphs that I have here, you have not only, you have to add the apparent change due to this horizontal misalignment to the real change. And that really masks the signal of the landslide in that area. So remember how Chelsea was talking about how we classify LiDAR points as ground, vegetation, or buildings? When that classification goes wrong, it can distort the digital terrain model. So a tree canopy point classified as ground inflates the terrain model. A building edge point leaking into the ground class creates strange bumps. These classification errors typically affect areas of meters to tens of meters and can create apparent changes of meters or more, especially around buildings. Finally, at the smallest scale, there's a geometric distortion from the scan angle. When the laser hits a steep slope at an oblique angle, the measurement is less precise. So this creates spatially correlated noise at the scale of terrain features. It's most pronounced on cliff edges and steep hillsides, so exactly the places where geomorphologists often want to measure change. All right, so now I'm going to talk about some of the tools that we've developed to address these challenges. So now that we've cataloged some of the types of error present, let's think about how we would go about quantifying their effect on vertical differencing results. So for very long-range errors that are almost perfectly correlated at the scale of our area of interest, we're interested in the vertical bias. That is the vertical alignment error that should be close to constant across the raster. For spatially correlated errors at the long, mid, and short scale, error magnitudes will change across the raster, so we'll quantify the mean uncertainty across the raster. Oh, sorry. This shows how we get the vertical bias. across an example in Indiana. So we'll take the median of the vertical differences with the assumption that over a sufficiently large area, the differences should be centering around 0. Okay. So yeah, for the spatially correlated errors at the long, mid, and short scales, error magnitudes will change across the raster. So we want to quantify the mean uncertainty across the raster that error types at each spatial scale introduce. To do this, we can model short scale, mid scale, and long scale correlation patterns of the differencing results. And we do that with a method called variogram analysis. So let me explain variograms because they're kind of the workhorse of our approach. So variogram is a tool from geostatistics, the branch of statistics that deals with spatial data. It answers a pretty simple question. So as you move farther apart in space, how different do the data values become? So here's a preview of what we're going to be building towards in this quick explanation. So a variogram plot that captures the spatial structure of error in our differencing results. So hopefully by the end of the explanation, you'll be able to read one of these. So let's start with something concrete. Here's a small patch of topographic differencing results displayed as a grid. Each cell has a value representing how much the elevation changed at that location. So red, again, means the surface went down. Blue means it went up. And the intensity tells you the magnitude. So it's a heat map of landscape change. Notice that the nearby cells tend to have similar colors. That's not a coincidence. It's a clue that the values and the errors are spatially correlated. So how do we measure that correlation? To build a variogram, we don't use every single cell. Instead, we sample a subset of points from the grid. These white circles represent our sampled locations. We sample because computing distances between every possible pair of cell in a large raster would be computationally prohibitive. For a 1,000,000 cell raster, that's 500 billion pairs that we'd have to be looking at. Our sampling strategy divides the raster into subregions and picks points within each one, so we get good spatial coverage without overwhelming the computer. So here's the key step. We start comparing pairs of sampled points. The arrows show the lag vector between 2 points. So the lag is simply the distance separating them. For each pair, we ask, how different are their values? We don't just look at one pair, we look at all pairs at a similar distance. So here you can see more lag vectors connecting various pairs of points. Each pair contributes 1 data point to our variogram. So for every pair, we compute the squared difference in their values. Pairs that are close together will tend to have small square differences because their values are similar. Pairs that are far apart will tend to have larger square differences. That trend is what the variogram is capturing. So we group all the pairs by their separation distance into a bin. Oh, sorry. For each bin, we average the square differences and divide that by 2. And so that'll give us the semivariance at each lag distance. So the formula you see here is the Matheron equation, the formula you see here is the Matheron equation, which you don't have to memorize by any means. It just is telling you how we're calculating this semivariance for each one of these bins. So we're going to start building the variogram plot on the right side of the screen. So each orange dot represents 1 lag bin, the average semivariance at that separation distance. So the x-axis is lag length or distance. The y-axis is semivariance. The equation at the top, again, is just the Matheron estimator again. So for m pairs at a given lag, we sum their square differences and divide them by 2m. So it's simple arithmetic, but very powerful when you see the patterns it reveals. So the first data points appearing on our variogram, notice that it starts low on the left. At short distances, points are similar, so the semivariance is small, and that's what we would predict. Nearby things are more alike. We repeat the sampling process multiple times, each with a different random selection of points, and average the results. So that will give us confidence bounds and smooths out quirks from a single random draw. So here we are filling in more lag bins. Oops. You can see the classic variogram shape emerging. So semivariance increases with distance. The curve is rising because as we compare points that are farther and farther apart, their values become less correlated. So the rate at which this curve rises tells us about the spatial scale of the error. A curve that rises quickly means correlation drops off fast, so errors are more localized. A curve that rises slowly means correlation persists over longer distances, maybe again from like flight line issues or large-scale misalignments. So we can, as we add more detail, we can pay attention to where the curve starts to level off. So that transition from rising to flat is one of the most informative features of the variogram. It marks the distance beyond which measurements are essentially independent of each other. Also notice the scatter in the data points. At shorter lags, when we have many pairs, the estimates are tighter. At longer lags with fewer pairs, there'll be more uncertainty. And you'll see that with some of the real variogram results that we look at. So now we have almost a complete experimental variogram. The pattern is clear, so semivariance is increasing from the left to the right, and then it stabilizes. This classic shape tells us there is spatial structure in our data. If the errors were purely random with no spatial correlation, the variogram would be a flat horizontal line at the data variance. So here, So now we need to fit a mathematical model to these experimental data points. So we annotate the key features we want to models to capture. So at a very short distance, there might be a jump at the origin called the nugget, representing measurement noise beyond the resolution of our grid. The overall rise represents the spatially correlated error, and the plateau represents the total variance in our data. So our goal is to find a curve that passes through these data points and gives us parameters we can use for our calculations. So we're highlighting where the data begins to stabilize. This region is critical because it defines the range, which is the distance at which spatial correlation effectively disappears. Beyond the range, knowing the value at one point tells you nothing about the value at the other point. So we can overlay a fitted spherical model. The spherical function is one of the most common variogram models because it rises smoothly from the nugget to the sill and has a clear finite range. It's like a gentle S-curve that levels off. The model parameters, nugget, sill, and range, each have physical meaning. The nugget captures very short range noise. The sill minus the nugget gives the variance from the spatially correlated process, and the range tells us the scale at which those processes operate. So the blue curve is our fitted model. Below it, I've added text showing the model type and its fitted parameters. So the range, which is the correlation distance, and the sill, which is the variance contribution. In practice, we test multiple model configurations and use statistical criteria to select the best ones. We want a model that fits the data well without being overly complex. So here is this sill and the range. And this is the final fitted variogram with all of its components labeled. So the range marks where the model reaches the sill, the distance at which the curve plateaus. Everything to the left of the range is within the zone of spatial correlation. Everything to the right is spatially independent. So from these parameters, we can propagate uncertainty for any area of interest. So larger areas will have lower mean uncertainty because correlated errors tend to average out. Smaller areas will have higher uncertainty because you're within the correlation range and errors reinforce each other. So computing variograms for millions of raster cells is computationally very expensive. So a current approach computes all pairwise distances and it requires storing an enormous distance matrix. So for 50,000 points, that's about 2,700, or sorry, for 10,000 points, that's about 2.7 gigabytes of memory and can take like in the tens of seconds. And again, 10,000 samples is a relatively small number of samples over an area. Our implementation uses 3 key optimizations. So first, we sample the raster directly rather than using every cell. We use a streaming algorithm that accumulates squared differences directly into lag bins in a single pass. So we avoid storing the distance matrix entirely. That drops memory use to about 0.2 megabytes, a reduction of 4 orders of magnitude from the current geostatistical software that's out there. And third, we use NUMBA just-in-time compilation and OpenMP parallelization to compile the Python code to machine code and distribute the work across CPU cores. So the result is a variogram computation tool that takes a fraction of a second instead of 10 plus seconds or minutes once you start adding more points, which makes it actually feasible to embed it in a web tool and also feasible to do analyses over much larger areas. So we don't fit just one model and call it done when it comes to variogram fitting. We evaluate nested spherical models with 1, 2, or 3 components, with or without a nugget effect. So again, that's the discontinuity at the 0 lag, which represents measurement noise smaller than our grid spacing. So we rank these models and balance goodness of fit versus complexity. And then we also run parametric bootstraps to get confidence intervals on our model parameters. So everything comes together once we kind of look at let's look at a model that has 3 spherical components. So our uncertainty decomposition has 4 layers, each building on the last. So again, first, the very long range. So that's with much higher ranges, you get the systematic vertical bias. Then at the mid-range, so again, hundreds of meters, you might have a component that expresses the mid-range sources of error. And then finally, at the short range, so meters of 10 to tens of meters, we're looking at kind of those short range error sources that we talked about before. We also take a look at uncorrelated random noise. So this is estimated as the standard error of the mean. And for large areas, it's typically negligible compared to the correlated error. So we combine all of these components in quadrature. That is, we take the square root of the sum of squares, which is the standard way to combine independent uncertainty sources. And it gives us a single number, the total mean uncertainty for a given area. So that expresses itself as like plus or minus 4 millimeters of error for a given area. So that's our confidence envelope. So if the observed change in an area is larger than this, we can be reasonably confident that it's real. If it's smaller, it's within the noise floor. Crucially, again, this uncertainty is area dependent. So a small polygon, say a single landslide, will have higher uncertainty than the full study area because there's less spatial average. We have a Jupyter notebook that takes you through this workflow and lets users calculate uncertainty for specific features of interest, which is essential for determining whether a particular change is statistically significant. So I'm going to now talk about an example that we applied our differencing and uncertainty methodology to. So this was last year. In January 2025, the Eaton fire burned about 57 square kilometers of wildland-urban interface in the Los Angeles County, causing 17 fatalities and destroying over 9,000 structures. It was one of the most devastating wildfires in California history. So these satellite and aerial images show central Altadena before and after the fire. The devastation to the built environment is immediately apparent at the scale of meters to tens of meters that we see in the differencing results on the lower right. But what happened to the landscape itself is also something we need to look at. So here before we were looking at digital surface models, here we're looking at digital terrain models where the main signal, so the burnt trees, have been removed. And we're actually interested in looking at hill slope and channel processes that have occurred during the fire. And those are much more subtle and difficult to distinguish from error. So that's where our tools will come in. I'll show you. So for the entire Eaton area and also for the Palisades fire, we differenced pre-fire LiDAR that we had from 2018 with preliminary post-fire LiDAR collected at the end of January, so just days after the fire. So here are the initial differencing results. And if we look at the variogram, it shows 3 correlation length scales. So one at 25 meters, one at 337 meters, and one at 1,863 meters. So that kind of hundreds of meter scale component, we can recognize that as the component at 1.8 kilometers, that's kind of classic flight line error. The one at kind of 300 meters is likely due to topographically correlated error. And then finally, the one at 25 meters is likely due to both real change and, again, those smaller scale error sources. So to get rid of the get rid of the horizontal error, that's one that we can easily fix by applying horizontal co-registration, so an alignment correction. And those are the results after the alignment correction. So we can look at the variogram results from this one, and we can see that the 300-meter scale component is gone. So that means that our correction worked. The correlation length was indeed alignment error, and co-registration removed it. So the total mean uncertainty dropped to dropped by about a couple centimeters over the entire area. So this is the power of the approach. The variogram doesn't just quantify the error, it diagnoses it. By identifying the spatial scale of each of the error components, we can target corrections and verify that they actually worked. So if a component disappears after a correction, we know we addressed the right problem with our correction. And we can also use uncertainty to look at specific kind of natural hazards questions. So this is a field photo from a burned hill slope that shows dry ravel, so small erosion channels that happen on the bare burned soil once the vegetation is removed. So this is a centimeter scale process in terms of like the vertical change that we're trying to resolve. So for the Eaton fires, entire hillsides were burned, so all the vegetation is removed. And if you imagine, then you get rain coming in from an atmospheric river, dumping water. What happens next is in the dams, in the channels created by all this material, you'll initiate debris flows, mud flows, and landslides. So kind of estimating the hill slope movement after a wildfire is really important for emergency managers in the area. So why don't we try to see if we can actually detect this change using LiDAR? So again, centimeter scale, centimeter magnitude vertical change. We delineated individual channel reaches and their contributing hill slopes and calculated the mean topographic change for each polygon with the propagated uncertainty that we got through our tool. So the hill slopes show a slight lowering of 1 to 5 centimeters, but the uncertainty is plus or minus 11 to 12 centimeters. So the signal is smaller than the noise, so we cannot statistically validate hill slope erosion at this scale. It's an honest result. Knowing the limits of what you can and cannot detect is just as valuable as the detections themselves. But on the other side, the channels show clear aggradation, so material accumulation of 17 to 33 centimeters, plus or minus about 13 centimeters. The positive signal exceeds the uncertainty envelope, so we can confidently say, yes, these channels receive sediment after the fire, which is consistent with dry ravel. Again, that gravity-driven transport of loose sediment from freshly burned slopes into the channels. This offers an opportunity to make volume calculations and see kind of how much material is susceptible to be moved during this during the next atmospheric river event. So our tool provides a quantitative answer with very rigorous uncertainty bounds for that question. So to summarize, LiDAR differencing is a powerful way to measure landscape change, but every measurement contains error at multiple spatial scales. Traditional approaches to remove data to deal with that error can bias results, but our geostatistical approach uses variograms to characterize and quantify error at each scale, preserving all the data while providing honest uncertainty estimates. So we've built this into a Python package, which is free and open source on OpenTopography GitHub. I will add the link to the package once we send out the slides later. And it's also integrated into our on-demand platform, which runs right here on the SDSC infrastructure. So whether you're a geomorphologist studying erosion, a hazard responder assessing post-fire risk, or kind of a homeowner interested in monitoring their infrastructure, you can use these tools to get rigorous uncertainty estimates without writing a line of code. So the Eaton fire case shows that we can resolve centimeter scale changes in channels with confidence, while honestly acknowledging where our resolution falls short. So that balance between detecting real change and knowing our limits is what good uncertainty analysis is all about and what we've implemented into OpenTopography. So thank you so much. The more kind of tutorials about how to use OpenTopography are available at opentopography.org. And our code, like I mentioned, is in the GitHub, which I will add the links to the distributed slides. And I'm happy to take any questions. Thank you.